And we are coming to the third lecture in this session. It will be given by Professor Kenjiro Terada from the International Research Institute of Disaster Science of Tohoku University in Japan. Dr. Terada's career began after he obtained his Bachelor of Science from Nagoya University in Japan. He pursued graduate studies at the University of Michigan, where he obtained his Master of Science and PhD degree. After that, he went back to Japan. At first, he worked at the University of Tokyo for several years, and then he moved to Tohoku University as assistant professor. Meanwhile, he has been promoted to full professor at this university. He has published extensively, about 180 refereed journals in both domestic and international journals. The main thrust of Dr. Terada's research is the development of mathematical models and of computational techniques for heterogeneous materials by means of computational homogenization methods. Recently, he also became involved in disaster simulation. Professor Terada is a member of the Executive Council of the ISCM, and he also serves as the Vice President of the Japan Society for Computational Engineering Science. So, Professor Terada, the floor is yours.
Thank you, Professor Mann, for your kind introduction. I'd like to thank the organizer of this conference for inviting me to this special event. I'm Kenjiro Terada from Tokyo University. Okay, I thought I was the last one, but okay. Today I'm going to talk about the advantage and challenges of the numerical material test, pre-and test, for computational homogenization. I first summarize the method of coupled two-scale analysis and specify some limitations. Then also I exhibit my preference for the method of decoupled approach over the coupled one. This decoupled approach hinges on the numerical material testing and also the numerical pre-testing. So I also discuss the advantage and challenges of these methods. We also talk about application of the isogeometric analysis to homogenization analysis and specify some problem related to the numerical modeling of unit cell. And then I provide one solution. Okay, let me first briefly review what is the method of coupled two-scale analysis, which is also called FE square. Most of you probably know this name. In this method, we using the macroscopic strain at each integration point in element of this kind of macrostructure, we solve this kind of microscale equilibrium equation to have the microscale stress here. Then we take the volume average of this microscale stress to have the macroscopic stress here. Then we repeat the same process for all the integration points to have the macroscopic equilibrium. Okay. So by this method, we don't need a specific form of the macroscopic constitutive equation. So this method is very attractive as a computational methodology. So that many researchers involved in this field of research. But unfortunately, this method is very not practical since it's very time-consuming, even if the parallel computations are applied. Also, it's impossible to be implemented into the existing C software. In addition, this method is valid only within the framework of mathematical homogenization. That is, the mathematical requirements such as local periodicity and separation of scale are satisfied only for weak nonlinear problem. So we cannot deal with the strong nonlinearity involving microscale cracking or microscale buckling or microscale cracking, which leads to the mesoscale strong discontinuity. So my assertion here is that the computational homogenization methods are applicable only mainly for the situation in which macroscopic constitutive equations are available or can be constructed with reference to the constitutive equation assumed at the microscale. So for that reason, I gave up use the method of coupled approach several years ago. Then, although I was the one was originator of this method, instead I'd been advocating the method of decoupled approach for two-scale analysis, which is based on the numerical material testing. In this method, I conduct the numerical material test before conducting the macroscopic analysis. This method have been studied and validated in these references. This flowchart shows the procedure of the decoupled two-scale analysis method. Here we have the unit cell of the fiber reinforced plastic type, which is composed of carbon fiber and also polycarbonate materials. And this unit cell is regarded as a numerical specimen in the numerical material test in order to characterize the macroscopic material behavior. Before conducting numerical material test, we have to prepare the data for the microstructure, such as unit cell, geometry, and also material model for the constitutive material used in the unit cell. In this example, we have the experimental data for the polycarbonate material like this. For these polycarbonate materials, we may be able to choose this kind of constitutive equation. This is the classical elastoplastic creep damage combined model, which exhibit weak nonlinearity. Since this model is very standard, so we don't need to explain the detail of the model, but these unknown parameters here, colored in red, have to be identified as some optimization method. Then, by identifying the material parameter of the assumed microscopic constitutive equation, we can conduct a numerical material test on this unit cell. For example, we choose 6 patterns of macroscopic deformation, then apply the unit cell to have this kind of macroscopic stress strain curve. These are the actual responses in X and Y direction. This is the response in Z direction. These are the macroscopic shear strain responses. Okay. As you can see, these exhibit strong anisotropy, which reflects the unit cell geometry like this. Okay. Then, next step is the determination of the macroscopic constitutive equation and also its material parameter identification. For that purpose, I'd like to advocate these answers. That is, the macroscopic constitutive law inherits the characteristics of microscopic constitutive equations employed for the unit cell. This assertion is partially validated in this article. Therefore, as a macroscopic material model, I may be able to assume or employ this kind of anisotropic version of elastoplastic creep damage combined model. Okay. This model is almost the same as the microscopic constitutive equation I assumed for the unit cell, okay, except for anisotropy. This anisotropy can be characterized with these Hughes tensor. Now, in this assumed macroscopic material model, we have 39 parameters. These unknown parameters should be identified by applying some sort of optimization method. In this example, we applied the particle swarm optimization to identify these parameters. These are the identified curve I obtained. This is the macroscopic stress strain curve obtained by the identified material parameters. As you can see, in comparison with the numerical material test result, identification was quite successful. Okay. Then we can conduct macroscopic analysis by using the selected macroscopic constitutive equation and material parameters. If necessary, we can also conduct a localization analysis like this. So, as you can recognize that the method of numerical material test is definitely a practical option for computational harmonization and got support, especially from the industry. Okay. But unfortunately, the macroscopic constitutive modeling based on the numerical material test is not always easy, okay, especially for the anisotropic finite strain framework. Let me look at this issue next. Suppose we are using a special type of thermoplastic resin for matrix material in the cell. We also suppose that according to the numerical experimental result, we may be able to, we may have to employ finite strain viscoelastic viscoplastic type combined model for resin material that can be characterized this multiplicative decomposition of the deformation gradient. This graph shows the objective stress strain curve of this thermoplastic resin in glassy resin, okay, which involves viscoplastic and viscoelastic responses. That is, we have here pseudo yielding, then subsequent stress softening, which is followed by orientation hardening like this. We also have to represent viscoelastic responses involving a homogeneous creep and also stress strain relaxation like this and stiffness reduction. When we use the classical generalized Maxwell model, we would have the functional form of the constitutive law like this. With this model, we can characterize the typical viscoelastic response, that is the dependency on temperature and also the deformation rate. For the viscoplastic part of the model, we may be able to use this set of governing equation. Here we have the back stress to realize this kind of orientation hardening in glassy regime. Then, by using this proposed finite strain viscoelastic viscoplastic model, we can conduct numerical test. Okay, this is in cell of fiber reinforced plastic composed of carbon fiber and thermoplastic resin. This is the information about the cell model. We have some 8-node hexagonal element like this. Then we impose 6 patterns of macroscopic. Maybe movie doesn't work in this case. So yeah, this deform by applying the macroscopic deformation. Then we could have the microscopic deformation with stress distribution in this case. Maybe the resolution is different from the projector, so I'm sorry for that. This is the corresponding macroscopic material behavior. That is the stress strain curve. Then, as you can see, we have the strong entropy. Okay, and also we have the viscoplastic and viscoelastic type model, which reflects microscopic constitutive equation I have assumed for unit cell. Okay. Then the question is, what is the corresponding macroscopic constitutive equation involving the finite strain, viscoelastic and viscoplastic type behavior? But more importantly, we had entropy. So we need an isotropic counterpart of the material model employed for the unit cell. That is, we should have an isotropic version of finite strain viscoelastic viscoplastic combined model. Okay, do we have it? There might be some, but they must not be versatile. So in that case, do we have to go with the F square? If you like it, go ahead, but I don't prevent. But I should say that I should make effort in formulating the anisotropic counterpart in view of practical application. This is our ongoing research, but I haven't yet there. So let me go on to the next topic, that is numerical pre-testing. The method of numerical pre-testing has been recently proposed by ourselves in this article. Then here, this is our problem setting. This is our numerical specimen, that is in itself, which has the periodicity in plane direction only. So we don't have the periodicity, the thickness direction in this case. Then by conducting the series of numerical material testing, then we can evaluate macroscopic plate stiffness for equivalent homogeneous plate. Okay. And more specifically, we impose the 8 patterns of macroscopic deformation on the in-plane cell like this. Then we can compute macroscopic resultant stress. Okay. Then, in this case, we solve this set of governing equation with this constraint condition, which correspond to the in-plane periodic boundary condition. Okay. Then by using equilibrium stress, we can compute the macroscopic resultant stress like this. Then let me show you a very simple numerical example with this in-plane cell. Linearly elastic materials assumed for both inclusion and matrix space. Then we impose 8 patterns of macroscopic deformation to this unit cell to have these microscopic deformations. Then we could compute the components of homogeneous plate stiffness matrix like this, whose non-zero component is given here. Then by using this macroscopic plate stiffness matrix, we can compute the macroscopic equilibrium state. This is a macroscopic model with plate elements. For the purpose of comparison, we also prepared 3D elements for the direct numerical simulation in this case. These are the macroscopic results. As you can see, the deformation is almost the same, so the reflections are almost identical. Then now, we can recognize that the mathematical structure of the numerical plate test is very similar to the classical homogenization theory, so we also can conduct localization analysis. Okay. For that purpose, let us pick up the macroscopic material point here, for example. Then, by using the macroscopic generalized strain at this point, then we can compute the microscopic mechanical behavior like this. These are the localization results. This is the corresponding local responses obtained in the direct numerical simulation. As you can see, the responses are almost the same. So we can recognize that everything seems to be fine for linear problems in this case. But how about nonlinear problem? How about a nonlinear numerical plate test with nonlinear material? In this context, let us look at this example problem. Here we have the target composite plate with a floor slab with asphalt mixture. This is the in-plane cell, in this case, composed of 3D solid elements and 3 layers here. Then one of the material here is assumed to be viscoelastic, viscoplastic material in this case. Other materials are simply linearly elastic. Then applying the 8 patterns of macroscopic deformation on this in-plane cell, then we can obtain this microscopic deformation. These are the corresponding relationships between the macroscopic resultant stresses and generalized strain, which exhibit weak nonlinearity. Okay. Then the question is it possible to determine a single material model from these relationships between macroscopic resultant stresses and generalized strains? The answer would be no. Then the next question, do we have a general nonlinear constitutive theory that relates the macroscopic resultant stress, not stress, resultant stress and the generalized strain? Answer would be no. Then what should we do? Do we go with a fifth scale? Maybe. But if not, what else? Okay. One of the solutions would be the replacement of this solid model by equivalent plate model. Okay. That is, we identified this in-plane cell model composed of 3D solid element by an in-plane cell model composed of laminated plate elements. That is, we use in-plane cell composed of laminated plate elements. Then we conduct the numerical plate test on this plate finite element. Then compare the result with the result of the solid elements. Then we can conduct the optimization analysis to identify the material parameters of each lamina of this element. Then this is the identification result. As you can see, the curves are almost identical. So identification was successful in this case. Then now we can carry out the macroscopic analysis with equivalent laminated plate elements here. This is the macroscopic model of the floor slab with bridge girder. In this case, applied load is given by this truck. Then this shows the macroscopic result. Again, we can't move the movie in this case. I'm sorry. But since the choice of element of material model are standard here, so we can carry out this macroscopic analysis by using any kind of finite element code. In this case, we have used ANSYS software. Then picking up some material points from the macroscopic plate model, then we can conduct the localization analysis in order to characterize the microscopic material mechanical behavior in this case. Okay. Again, we cannot have the moving deformation. But here, we have succeeded the two-scale plate analysis of floor slab. Then, more importantly, I'd like to assert that I have insisted on performing the decoupled analysis. So I didn't use FE square even though the problem is nonlinear. Then let me go to the final topic, is the isogeometric homogenization analysis for computational homogenization. Before going to the next, this topic, let me briefly carry out the numerical material test in the context of finite element method. Given the numerical specimen here, this is a finite element model of this cell. Now with the information about geometry and material at the micro scale, then we can compute the macroscopic stress from the macroscopic strain, okay, by solving this kind of governing equation, microscopic equilibrium equation. Here we note that we have the constraint condition on the set of relative displacement on the opposite side here, which corresponds to the periodic boundary condition. Okay. More specifically, in the actual implementation of this periodic boundary condition, we have to introduce these external points here, each of which has degree of freedom of relative displacement on the opposite side. Okay. Then the reaction force here, evaluated at these external points, can be used also for the calculation of the macroscopic stress in this case, okay, without performing any volume integration. Okay. Then within this framework, we can apply the isogeometric analysis to the numerical material test and also the numerical plate test. Here we have the nerves-based function as usual. We don't need to explain the detail here. Then we can represent the geometry of the microscopic displacement like these expressions here. Then, since the basis function have local support property, not span whose length is non-zero can be recognized as an element in this case. So that we have the approximation of the displacement. This is microscopic displacement in element, and also we have the microscopic strain of this form. Using these approximation of the microscopic deformation, we have the discrete form of the microscopic equilibrium equation here. Then let me specify the problem in the modeling of the unit cell for the isogeometric analysis. Here we have the isogeometric mesh in a parameter space. Then we can generate the isogeometric mesh of unit cell of this type in physical space here, which usually are rectangular parallel pipe like this. Then pick up two elements here. These are the common control points, so we don't care about this. But look at these two control points, which is not common, but overlapped here, in order to make angular point. Okay. Then in this case, we should have the continuity equation of the control displacement of this control point here. This one, but this one can be satisfied without any constraint condition due to the feature of the isogeometric analysis. But at the same time, we have to impose a periodic boundary condition with these external points here in order to conduct a numerical material test. Okay. So look at these external points. Then the periodic boundary condition for these angular points must become this set of multiple point constraint for periodic boundary condition. Then applying equivalent transformation, we could have this set of multiple point constraint for periodic boundary condition here. Then we can recognize that the control point convex closure for the control points 1, 2, and 3 becomes a straight line. This is due to the convex full property of the isometric analysis. This implies that the higher order deformation cannot be realized along this edge. Okay. Same situation can be applied those edges. So we can't have the higher order deformation along the edge of the unit cell in this case. So the numerical material test would provide a much stiffer result than reality in this case. So we have to resolve this problem. So in order to realize a higher order deformation in the unit cell deformation, we would have two options in this case. One of them would be the use of the multiple knots. Okay? That is, we repeat the knot value here to have the additional control point here, to have the higher order deformation along this edge. But in this case, we have discontinuity along this line. This is the interface between the separate elements. This is not preferable. Okay? But worse than that, the knot repetition is very cumbersome. That is very hard to handle because the modification of the model is very difficult in this case. So let us look at the second option. This is the multiple patch strategy, which requires us to have the multiple patch division like this. Here, the difference in the color indicates the different patches here. But in this case, also we have discontinuity along this edge. This is the interface between separate patches. But it's very easy, rather easy to handle, deal with the heterogeneity in the unit cell and also the modification of the material model. Okay, so we'll take this option. However, okay, we also have to impose a periodic boundary condition, not only periodic condition, but also the jointing condition between separate patches. This is a resulting set of multiple point constraints in this case. Then applying the equivalent transformation in this case, then we have this set of multiple point condition, constraint condition for the periodic boundary condition, also the jointing condition. Then in the actual implementation of this constraint condition, we may employ this master-slave techniques as usual. Then both the master and slave control points for multiple point constraint associated with the periodic boundary condition would become the master control points for jointing condition. So we have to employ the double multiple point condition in this case. So by using the multiple patch strategy with double multiple point constraint, we may conduct a numerical verification. This is isometric mesh in this case. This is the corresponding multiple patch. Okay. We compare the result with the finite element model here. We also have the hexagonal 8-node and 20-node hexagonal mesh. By applying 8 macroscopic deformation pattern, we have with microscopic deformation. Then you would have these components of the plate stiffness, homogeneous plate stiffness. As you can see, since we assumed the second order Nab's function, I forgot to tell you, I assumed in this case second order Nab's function for the isometric analysis, then the result of this one is almost same as this finite element analysis result with 20-node hexagonal element. Okay, this is the last example, isometric analysis for nonlinear material numerical model. Then this is geometric mesh with elastoplastic matrix material on the linear elastic fiber. This is the patch division. Here is the numerical material test result with multiple patch modeling. In order to demonstrate the performance of this multiple patch modeling, I also conduct the numerical material test with single multiple patch modeling. As you can see, we don't have the appropriate shear deformation in cell in this modeling. Okay, this is the macroscopic response by the isogeometric homogenization analysis. Now let me conclude my presentation. I have demonstrated the method of the coupled two-scan analysis is promising if numerical material tests and numerical plate tests are successfully conducted. Then we also discussed the advantage and challenges of numerical material and plate tests. Then finally, I introduced our final first trial of isogeometric analysis for computational homogenization. In particular, I introduced multiple patch strategy with double match point constraint in order to cooperate with the periodic boundary condition and jointing condition of between separate patches. Thank you for your kind attention.